Hey everybody, my name is Param Damle, and welcome to a course on quantum machine learning. I originally taught this course at the University of Virginia in spring of 2024 with Professor Gianluca Guadani for the Graduate School of Data Science. I wanted to present it online today just to help other learners out there interested in quantum computing, machine learning, and the intersection of these two very big fields right now. So let's get started. A little bit about the course. I tried to break it up into three distinct phases. The first phase is generally to get you caught up on quantum computing. This course doesn't assume that you know anything about quantum computing. I think that's what makes it such a great introduction to the field. And then the second phase, we're going to start to understand a bit more about what we can do with quantum computing. So learning a bit more about the quantum algorithms that have been popularized over the past couple decades. And then in the last phase of the course, we're going to go into the intersection of quantum computing and machine learning. An important thing to note about this course is that we will be focusing on the math and the computer science aspect of quantum computing instead of the physics side, so don't expect to know much about wave functions or Schrodinger's equation or anything like that. So why do we want to study quantum computing? Well, there's a couple reasons, but the primary reason most often provided is that the special properties of quantum computing, which we're going to learn about later, that include superposition, interference, and entanglement, let us solve problems differently than traditional classical computers. Some examples include threatening to decrypt major cryptographic standards that we've had for decades, including the famous RSA encryption. And a major thing we're seeing across the world is that a lot of adversaries are recording a lot of encrypted data that they can't quite process in the near term, waiting for quantum computing to really take off, have ways to decrypt these ciphertexts efficiently in the future and essentially crack things that they're not supposed to crack way later down the road. This strategy is called harvest now, decrypt later, and we'll talk a bit more about it when we go into quantum cryptography. Another important use case for quantum computing is modeling physical, chemical, and biological phenomena that aren't as efficiently modeled using these classical simulations of physical phenomena, and instead quantum computers let us approximate these relationships between particles that act in a quantum way. Also, as you may know, both quantum computing and machine learning are both very fastly expanding fields, particularly within mathematics and computer science. So knowing how these two things could relate to each other can open doors for either opportunities or research avenues, should you be interested in going down that path. An important thing to note, however, is that not all problems are just going to be exponentially sped up by quantum computing. There's many things that classical computers are pretty good at already, and we don't really need quantum computers for these use cases. This includes anything involving input-output, anything involving real-time communication, or things that are just computationally simple like many sorts. So let's delve into quantum computing a little bit, right? First, let's talk about what classical computing is like, the computing that we all know and love. So on a classical wire, we have these bits that can either be 0 or 1. And when we read the values off the wire, we can consider that we're measuring the value of the system. And with classical computing, this is deterministic. We know that if our wires have value 101, there's a certain way that the current is flowing on those wires. And when we measure all three of these, we're going to get the value 101. And when we convert this from binary to decimal, this means that this entire 3-wire system has the value 5. Quantum computing, however, lets us superpose different values on top of themselves. So now, instead of the top wire carrying the value 1, it carries the value 0 half the time and the value 1 half the time. And so what we now get is that instead of a deterministic output, when we measure these 3 wires, half the time we're going to measure the value 001, which is equivalent to 1 in decimal, or the other half we're going to measure the value 101, which is equivalent to 5 in decimal. As for how we can represent qubits holding multiple values at once, we're going to get into that later. Now, when we combine multiple qubits into one state, we call that a quantum state. And sometimes these states can be independent. And that means that there's no relationship between the different wires. So if the first wire has a 50-50 chance of being 0 and 1, that won't affect the third wire, which has a 1/3 chance of being 0 and a 2/3 chance of being 1. So when you measure these, what do you notice about the distribution of the different states that we could measure off of this system? For those of you that have studied probability, you might be able to tell that with independent events, the probability of any specific outcome is the product of all the individual probabilities. So here you can see that the probability of reading 101 is just the probability of reading 1 on the first wire times the probability of reading 0 on the second wire times the probability of reading 1 on the third wire, which in this case is 1/2 times 0 times 2/3, which is just 1/3. But that's not always the case when it comes to quantum states. So sometimes the values on the different qubits on the different wires are not independent. And so what you get is something that you can't really break apart as easily. In this state, we have a 50% chance of reading 010 and a 50% chance of reading 101. And if you'll notice, if these states are dependent, we can't break apart the probabilities into a product. The probability of the first qubit being 0 is affected by the probabilities of the other qubits' values. So in this case, if we were to just simply multiply the probability of reading any specific value from any specific qubit, that would tell us that the probability of reading 101 is 1/2 times 1/2 times 1/2, which are the distinct probabilities of reading 1 on the first wire, 0 on the second wire, and 1 on the third wire. But we know that's not the case because we clearly see that we have a 50% chance of reading 101. Before moving on, let's talk a bit about complex numbers because these are immensely important when it comes to quantum computing. So you may know that a complex number can be represented by a real and imaginary component as a plus bi, and that we can plot this number on the complex plane, where the blue line you see there, the horizontal axis, is the real axis, and the vertical red line is the imaginary axis. So the point 3 plus 4i can be plotted as a 3 on the real axis plus 4i on the imaginary axis, and we can represent it as this vector here. You may have also heard of this term conjugate. So the conjugate of a complex number is simply inverting the coefficient on the imaginary part. So when you see this asterisk here next to a complex number, you know that you just have to flip the imaginary part. So if you had a plus bi before, now you're going to have a minus bi. So that's equivalent to reflecting the vector in the complex plane across the real axis. So you'd be turning plus 4i into minus 4i here. Another important concept and a parallel to regular linear algebra is that the norm of a complex number is just the magnitude of this vector that we've drawn in the complex plane. So if a value is a plus bi, we can either get the norm by the square root of the number itself times its conjugate, which itself is equal to a squared plus b squared. And I'll let you work out that math yourself. Furthermore, some important notation that you're going to see later in the slides is that the set of all possible complex numbers we're going to denote as C, and the set of all n length vectors of complex numbers we're going to denote as C to the power n. Next, let's refresh on some linear algebra concepts that are going to be necessary later down in this course. So a vector is a column of values, and when it's a complex vector, it's a column of values in Cn. So the vector we see here in C4 is a vector of 4 values, each of which is a complex number. A matrix, we can say, is a 2D collection of values. For example, the identity matrix is a matrix where every value is 0 except the diagonals, which are all 1. In this course, for disambiguation, I'm going to denote matrix multiplication with this bullet symbol, just so it's a thick, fat dot that we can use to denote two matrices being multiplied, where the rows of the first matrix are multiplied by the columns of the second matrix, like so. Other important notation in this class includes bracket notation. So, for example, a pure n-bit quantum state can be represented by a vector in c to the 2 to the n. So, this exponential factor obviously means there's a lot of values in this vector. And sometimes it's not super easy, especially when you're dealing with n equals 4, right? All of a sudden you're writing 16 element vectors everywhere, and that's not very conducive. So what we're going to do is we're going to use this notation, ket A, which means that it's a column vector of all zeros, except there's a single one at index A, where A is some binary number. And we're going to start with index 0. So when we have ket 0, we're going to have a 1 in index 0, which is the first index, and 0 is everywhere else. When we have ket 1, we're going to have a 1 in the first index, and 0 is everywhere else. When we have ket 0, 1, right, the fact that this is 2 qubits means that the length of the vector is 2 to the power 2, which is 4. And a 1 means that there is a 1 in the second index. Remember, we start from 0. So the rest of the values are 0 here. When we have ket 1, 0, right, this value equals 2, and we know that the length of the vector is 2 to the power 2, which is 4. So it's a 4-length vector of zeros with a single 1 at index 2, which is, again, the third index. So let's ponder an exercise. If A is an n-bit string, so there's n digits in A, ket A is part of what set? Well, if you answered the set of 0 or 1 to the power 2 to the n, you'd be correct, because each digit in our vector is either a 0 or a 1 because it's a binary vector. And there's 2 to the n many values in our column vector. An important thing to note here is that ket 0, 1 and the vector 0, 1 are not the same thing. Remember that the value inside the ket is actually the index of the single 1 in the vector. So ket 0, 1, 1, 0, 1 is the same as ket 13, which means if we have 5 values here, that there's 2 to the 5 values in our vector, which is 32 values, and there's a single 1 at index 13, which is the 14th value. So it's not the vector 0, 1, 1, 0, 1. Furthermore, it's important to consider whether the vector 0, 1, 1, 0, 1 could even be represented in ket notation. And why not? Well, as you may have figured out, is because all the lengths of the vectors that are produced using ket notation are a power of 2, and 5 is not a power of 2. Other important notation we're going to see later is that of the Hermitian or conjugate transpose of a matrix, of a vector, anything else in the complex 2D space. So denoted by this little dagger right here, the conjugate transpose of a complex vector is simply conjugating all the complex numbers inside it and transposing it. So rotating it around its diagonal. A column vector will become a row vector will become a column vector. If it's a matrix, all the values in the matrix will flip across the diagonal. Important thing to note with this equality here is that the order doesn't matter. So if you do conjugate all the values and then you move them, or you move the values first and then get all their conjugates, you're going to get the same exact result. Last thing I'll mention is that we denote this chevron and stick shape as a bra. So in bracket notation, the bra is a row vector, which is the conjugate transpose of the ket, which is a column vector. Another important concept that's a bit of a carryover from regular linear algebra is a dot product between two vectors. So if you have two column vectors, ket alpha and ket beta, the inner product, which is cleanly represented like this, is actually the conjugate transpose of the first vector times the second vector. So here, if we just have two generic column vectors, getting the inner product, or the dot product between them, is just getting the conjugate transpose of the first. Notice that a column became a row, and that all the pluses became minuses, right? Multiplied in regular matrix multiplication style with the other ket vector. So here we can get the pairwise product and then sum of that of the two vectors. Note, just like in regular linear algebra, if two complex vectors have an inner product of 0, we consider those to be orthogonal. And you might have learned this as perpendicular vectors in the real space. Also, note dimensions, right? If we have a ket times a bra, this is a column vector times a row vector. So we're going to end up getting a matrix instead. And when we have a bra times a ket, we're going to have a row times a column, and we're going to end up getting a single scalar value. Alright, let's do some quick fun exercises. You can pause the video now to quickly go through these, but I'll just go through the answers one by one and quickly explain how I got there. So first up, what is the conjugate of 2 minus 3i? Well, we just have to flip the minus to a plus, and we get 2 plus 3i. Second, what is the norm of negative 5i plus 12? Again, remember the norm is basically like the length of the hypotenuse, so we're going to use our trusty square root of a squared plus b squared formula to get 13. Next, what is the value ket 110? Now remember, the value inside the ket is a binary notation for the index of the 1. So converting 110 from binary, we get 4 plus 2, which is 6. Since there's 3 binary digits, we know that there's 2 to the 3, 8 positions in our binary vector, and the value at index 6, which 0 indexed is the 7th position, is going to be a 1. So I wrote it here as a row vector transpose for brevity, but what you see is a column vector of 8 values where the value at index 6 is a 1 and everything else is a 0. Next up, what is the inner product between ket 1001 and ket 1010? Well, remember that the two values there are the indexes of the 1. And since those two values are different, that means when you're multiplying each item against its corresponding item in the other vector, the two 1s are not going to line up. They're going to be in different indexes. So those two 1s are going to get multiplied by zeros, and all the other values are also going to be 0. So what we get is the entire inner product is 0. So these vectors can be considered as orthogonal to each other. Lastly, not to be scared by this super long equation, we just have to FOIL like we would with any other multiplication. And what we see here, again, like the last problem, is that none of the indexes on the right side line up with index 1101. So that value is going to get multiplied with a 0 on the other side. 10010 lines up with this value. So the only two coefficients that are being multiplied are I and 4i. And so the result is negative 4 ket 10010. Another thing we should discuss is that in this course, we're going to often see quantum states as probability distributions over possible outcomes. So, for example, if our quantum state has a 50% chance of being measured as ket 01 or ket 10, what we're going to see is that it's going to have a coefficient of 1 over square root of 2, and we're just going to add up the two vectors. Note that the zeros add up to 0, and the individual values in these separate indexes can all get added together into this resultant vector. Now, how is this a probability distribution? Well, the L2 norm, or the magnitude of our qubit, must equal 1. So remember how we had norms of individual complex numbers? Well, if we take those norms for each of the values in our qubit vector, we square those, add them up together, and then take the square root, that value should equal 1. But more importantly in this class is that we don't care about this square root. So what we say is that when we square all the norms of all the complex numbers in our vector and we add them together, we should get 1 as a result. So now, using this as a hint, what do we think the probability values for each of the indexes in this quantum state are? Well, if you guess that it's these individual squared norms, you'd be right. So the probability of measuring 0, 0 in this state is 0, but the probability of measuring 0, 1 is the norm of the value square root of 1/2, which is just square root of 1/2 squared, so it's 1/2. So what this state is essentially saying is that there's a 50-50 chance of measuring 0, 1 or 1, 0, and no chance of measuring 0, 0 or 1, 1. Now that last example was all real values, square root of 1/2. What if we add an imaginary component, right? What if our values are complex numbers? Well, remember, we just take the norm and we square it. So the norm of I over 2 is just 1/2, and squaring that, we should get 1/4. Again, note that this still obeys the property we talked about before, where all the squared norms should add up to 1 in order to be a valid probability distribution. Now note that since this is a distribution, we can keep measuring the state repeatedly and get a similar distribution of values, but we'll never truly know what the actual coefficient on any of these values is. So remember those wires from the beginning of the video. If the probabilities were instead 0.49 and 0.51, we'd probably keep measuring them 50-50 and we would never know the exact coefficient on any given index. Furthermore, because of this norm factor here, right, I over 2 is the same as negative I over 2, which is the same as 1/2, which is the same as negative 1/2, because all of those would produce a norm of 1/2. So if our particular state is phase shifted, right, if it's multiplied by I or negative I or plus or minus 1, we'd have no way to measure that, because what we're actually measuring is not the coefficient here, but we're measuring the index 0, 0, index 0, 1, index 1, 0, index 1, 1 with probability 1/2, right? So no matter what the phase shift is, if the likelihood of measuring that index is the same and all we see is that index, we can't really distinguish these different coefficients. Lastly, let's quickly touch on unitary operations. So a lot of the things we're going to be doing in these quantum circuits are going to be unitary operations. So unitary operations need to preserve the L2 norm of our quantum state. Why? Because we want to make sure that even before and after we apply these gates in our circuit, everything is a valid quantum state that represents a probability distribution. So the L2 norm needs to always add up to 1. So in our circuit, we're going to have these quantum state vectors V, these column vectors, and we're going to multiply these matrices U, which are these gates, kind of like logic gates in a circuit, in order to get some resultant quantum state that we want to measure and get some information from later on. So what are some properties of these gates that make them so special, that make them take in a quantum state and always output a quantum state? Well, there are a couple of properties that I've collected below, and all of these statements are mathematically equal to each other. So there's a way to start from one statement and assert that another statement must be true. First of all, as we stated above, the gate preserves the L2 norm, the magnitude of our quantum state. So no matter what gates we apply, no matter what quantum gates we apply, the probability distribution property is maintained. Second of all, if you multiply a gate with its conjugate transpose, it's equal to the identity matrix. Remember the matrix that when you multiply with a vector, returns that same vector that was inputted, right? What does this tell us about these unitary gates in our quantum circuit? Well, it hints that every unitary gate has an inverse, and that inverse is just its own conjugate transpose. So if you were to apply some gate U onto a quantum state by multiplying it, and then you apply U dagger to that result, you're going to end up getting the same state you had at the very beginning. And this is a very important property in quantum computing, that almost all actions should be reversible. Now, if you take the rows of any quantum gate, of any unitary matrix, and collect them into a big set, the set should be orthonormal. And what that means is that all of the vectors within this set, all of the rows of U, should be orthogonal to each other. So if you take the inner product between any two vectors here, you're going to get 0. And the set should be normal, which means that every single row should have an L2 norm of 1. This is also true for the columns of U. So if you take all the columns and split them apart, they should all be orthogonal with each other, and the magnitude of each one should be 1. Again, all of these properties are equal to one another. So if you want, as an exercise, you could try to get from any single one of these from the other, but it is possible. In the next video, I'll be covering a bit of the homework for this class, so I want to intersperse the lecture with some practical walkthroughs of the homework, which will be linked below. And a couple things you might want to do before getting started on that is making sure you have your local environment set up, whether you're working on Python and Jupyter locally, or whether you're working on a cloud service like Google Colab, which I highly recommend. It's what I use to make the homeworks, and it's worked very well for me in the past. Also note that it's nice if you learn how to work with LaTeX and work with writing succinct mathematical responses, because that'll help create this little portfolio of quantum computing throughout this course. Thank you for watching. Be sure to leave any questions or comments down below in case you found anything helpful, anything confusing. It'll help a lot for the next video. Thanks.